Imagine a land where cows are intellectual beings, where cows have the ability to create the basic building blocks of words, the alphabet. Now, the alphabet happens to have the same characters as the alphabet, just not necessarily in the same order. Farmer John gives us two things, the alphabet and a random string he wants us to spell with the alphabet. We want to see how many times it takes to go through the alphabet from left to right to spell the characters in the string. Let's look at the code. The idea for this is pretty simple. Just simulate the situation. Keep on looping through the alphabet until the word is spelled. First, we take in the input, the alphabet and the word. Then initialize an index counter for the word, and a variable that counts the amount of loops. So while the word is not yet spelled, or in other words, the word index is not the length of the word, we want to keep on looping through the alphabet. Within the alphabet loop, if the current character in the word is equal to the character in the alphabet, we can move on to the next character in the word. And then we increment the total loops variable after every time the loop runs. And then we have our answer, the total loops. For problem 2, you're given n numbers. You want to find a way to combine the numbers to form the maximum number of groups with the pattern even, odd, even, odd. To make our lives easier, let's say that even number equals e and odd number equals o, so that our desired pattern is EO. So to solve this, you have to first realize several properties of even and odd numbers. If you add an even number to some other number, the parity, the state of being either even or odd, remains the same. E plus E is still E, and O plus E is still O. If you add an odd number to another number, the parity changes. So O plus O changes to E, and E plus O changes to O. Knowing these properties, we can simply keep track of two variables, how many even numbers we have, and how many odd numbers we have. To form the maximum amount of groups, we want the groups to be as small as possible. We can just simply subtract 1 from our even count when we need an even, and subtract 1 from our odd count when we need an odd. Here's where it gets fun, when we run out of numbers. If we run out of odds, and we need an odd number, just give up. There's no way to form an odd number out of even numbers. And you can just add the remaining even numbers to any other group without changing the parity. If we run out of evens and we need an even, just use 2 odd numbers. If you only have 1 odd number though, you can't simply give up peacefully like you did with the even numbers. If you put it at the end, you don't form a perfect EO pattern, and if you combine it with any of the other numbers, it ruins the pattern. The only way to add it to the list is to combine it with the last odd number to form an even, and then combine that even wherever you want. So let's look at the code. We initialize our variables, total odds, total evens, and n, which is the total numbers we have. We take in our input, n, and take in n numbers, counting the number of even and odd numbers. Then we want to keep on making the groups as long as we have numbers left, or in other words, keep on running the loop as long as total odds or total evens is greater than 0. If we want an even group and total evens is greater than 0, we can use one of the even numbers to form a group by itself. Otherwise, if we have no more even numbers, we form an even number with 2 odds. But if we have only 1 odd left, we have to combine the last 2 odd numbers to make an even number, and combine that with any other group. When we do that, the total number of groups we have decreases by 1, and we stop the loop since we have no more numbers to work with. If we need an odd number, we use an odd number if we have one. But if we only have evens left, we give up, unless one of the intellectual cows somehow tell us how to make an odd number with some even numbers. For this problem, you have to find all possible ways to put a list of cows with a certain height into a row of stalls that also have a certain height. A cow can only fit into a stall if its height is smaller or equal to the height of that stall. Honestly, if I were a cow, I would fit into all the stalls. Can relate to that tiny cow over there. Anyways, to solve this problem, you can use permutations with a twist. Let me explain. To find out all the possible ways to arrange these 4 cows with no height limitations, you can think of it like this. There are 4 possible stalls to put the 4th cow, and after it occupies a slot, that leaves 3 possible stalls for the 3rd cow, 2 for the second one, and finally 1 for the last one. That's 4 factorial, or 4 times 3 times 2 times 1 possible permutations. For this problem, however, the cows can only occupy the stalls that they can fit in. So here we have the same cows, but with height limitations on the stalls. The cow with height 8 can only fit in 2 possible stalls, and after occupying 1, it leaves the cow with height 5 2 possible stalls, who leaves the cow with height 4 1, and the last one obviously only has one option. We then multiply all the possibilities together to arrive at our answer. Notice how both the stalls and the cows are sorted by height so that we can easily see the stalls that the cows can occupy. This time, we initialize global variables since we're going to use a helper function and we're going to access those variables in the helper function. In main, we start it by taking input into n and the heights of the cows and the stalls. Then we sort the arrays. Starting from the largest, tallest, I promise I'm not fat shaming here. We want to see how many stalls each cow can fit in, calculated by the valid stalls function, and multiply the resulting numbers together. Make sure to use long for the result, as it might exceed the integer size limit. In the valid stalls function, we start from the index passed in, which represents the rightmost stall left over, and then, using the fact that the array is sorted, count the number of times that we have to go left until we see a stall that is too small. Then we can just return the number of stalls, and then I guess that's it. The problem solved. Honestly, I was way overthinking this when I did this in comp.